Okay, so we're going to finish off our implementation of the A-star algorithm that we started in class. We're actually going to restart from the beginning, and I just want to make sure that everyone's on the same page about how this is implemented. So first, open up an IDE like Mu and make sure you save a empty document as AI pathfinding. And we're going to first start with importing a few modules. We're going to import Pygame. As you guys know, this is just the GUI for game development. So this is for graphical user interface of our algorithm here. We're going to import Heaps, which I'll explain in a bit what that does. But basically, you can think of it right now as a smart to-do list that always gives us the most urgent task. And it helps us decide which square to visit next on our map and to get to our goal faster. All right. Let's put a note here. This helps us with sorting the nodes we'll explore. Okay. And then we're going to import random, and we've used that many times before as well. We're going to use this to generate random numbers, which we'll use in our A-star pathfinding demo here. Okay. All right. You can save this. And really quickly, I want to talk a little bit about Heaps a little more. So a heap is another kind of data structure. You guys have learned about lists and dictionaries and tuples and sets. A heap is a way of representing a tree in memory. So there's two kinds of heaps. There's a min heap and a max heap. We're going to actually be using a min heap in our program. A min heap is really useful for implementing something called a priority queue, so that items that have higher priority are always sorted at the top of our tree structure. You can see here this list of items with a 2 at the top is the highest priority. This is how it's actually stored in memory. 2, 3, 6, with 3 and 6 being the branches off of 2, and then 8, 10 as the branches off of 3, and 15, 18 is the branches off of 6, and then 20, 25 is the branches off of 8. So you can see it again here if that was difficult to follow with another min heap here. So 9 is at the top of our tree, or the root of our tree rather. We got 12 and 20. So we left and then right always. So 12, 20 in our actual list in memory. And then again, we add a 14, it's going to go left again. And then we add a 21, it'll go right, okay, to add the children to 12. All right, I'm going to actually show you how the Heaps module works in Python. So I'm going to go back over to Python and open up REPL, or if you're using Dony, you can open up the shell, or you can do that in Visual Studio Code as well. So I'm going to import Heaps here. And then I'm also going to create an empty list that I'm going to call my heap. Okay. Now that we have the empty list, now what I'm going to do is push onto this heap. So I'm going to say heap push to the name of the heap that I'm going to push onto, and then I'm going to push something onto it. So I'm going to push on a 25. Okay. And let's say heap 20, 15, then 10, and then a 5. Okay. All right. So if we look at my heap, here, our root is 5 because this is a min heap. It has 2 branches, 10 and 20. And then 10 has 2 branches, 25 and 15. Now, in general, it doesn't really matter what the branches are. The heap always makes sure that the smallest element is at the top. So you notice that 15 is down here. But if I pop off of the heap, if I say heap pop, and then I say my heap, it'll pop off the 5, it'll pop off the 10, it'll pop off the 15, even though 15 was the branch off of the 10 before, okay? Even though it was down there, okay? Now it'll pop off and actually before I pop it off, let me show you what the heap looks like now. It has 20 and it has 1 branch, okay? So that's how we're going to keep track of the priority of what cell to look at when we're working on our algorithm, okay? Just wanted to make sure you guys understood that before we actually delve into this, because we'll be using this data structure quite a bit in our algorithm. All right, so now that we have our imported modules, now we're going to initialize Pygame. So that's just like turning it on so that it will take commands. So initialize Pygame, you're going to say pygame.net. All right. Now we're going to set some constants for our game. So we're going to set a window size, and then we're going to set a grid size for how many squares to fit on our game window. And then the cell size basically is going to be the size of the squares. So these are constants. As I said, window size is going to be a tuple with 500, 500. Our grid size is going to be 10 for right now. You can change that to something higher when you want to play with it, but we're going to start with 10. And our cell size is going to be our window size divided by our grid size. Okay. Remember, 2 slashes does division without a decimal point. Okay. So now that we have this, we're going to define some colors for our game. So we're going to have a red, green, blue, and white and black. Okay. As you guys remember, we define colors by using RGB values, red, green, blue. Let's do that. Let's start with white, and then black, and then green, and then red, and then blue, and then yellow. Okay, so let's define yellow here. We're going to say it's 255. Yellow is red and green together, so we have 255 for all the way on again, and then 0. Okay, so for blue, we have 0, 0, and 255. Okay, for red, we're going to have, and let me put this up here so it's clear. This is red, this is the green color, and this is the blue color in the tuples that we're creating here. 255, 0, 0 for red, and then green, it's going to be 0, 255, and then 0. And black will be 0. We got a comma there. 0 and 0. And white will be 255, 255, 255. Okay. All right. Now that we have our colors, the next thing we need to do is initialize our screen. Going to initialize screen, basically setting the stage for our game. We're going to say screen is equal to pygame.display.setMode. And we will send over to that method our window size, the tuple that we have in that, and the window size constant. Next, we have pygame.display set caption. And this will be the title of our window. So A star pathfinding. Okay. All right. As you guys know, at the end of all of our Pygame programs, at the end of our game loops, we're going to have pygame.quit. That will make sure that is always at the bottom of our program. At this point, we can actually run it to make sure that the window is going to be created properly. So I'm going to run it here. Okay, so I do have an error somewhere. Yes, I defined our cell sizing correctly. So because this is a tuple, what I need is the first item in the tuple. So I need to get the first item so I can divide by 500 here. Okay, so now I'm going to write it, and so now I'm going to run it, and this is what we get. We get a Pygame window. Okay, so I'm going to close this and stop that. And next, what we want to do is actually define our game loop. Okay, we're going to say here, this is, as you guys know, this will run continuously as our game is running. This is our main loop, and we're going to say running equals true, and then we're going to say while running. Okay, all right, so first inside of our game loop, what we want to do is set up some event handlers. Our program's going to wait to see if a mouse click or keyboard is pressed, etc., and reacts accordingly. For our game, we're going to mainly be looking at two things. First, we're going to look at if the user closes the window to stop the game, and if the user presses any key to start our algorithm running. Okay, we're going to say here, let me make a little space and bring this up a little bit and actually make this a little bit larger. I'm going to say for event.get, we are going to say running equals, actually we're going to say, we're going to say ftype equals pygame.quit. Then we're going to say running equals false, which will stop our loop. Also need to check for button presses. So we're going to say fevent type equals, and this should be double equals for equals instead of singles, equal sign, which is assignment, but then pygame dot key down. Okay, so now dot key down. All right, so now what we are going to do is actually put all our code inside of this if statement. So all of our code is actually going to run inside of our if statement for our implementation here. At first, what we want to do is once the key is pressed, we want to randomly generate a start and ending point or start and a goal for our pathfinding algorithm to work on. So inside of our grid, our 10 by 10 grid. All right, so this is that each time we press a key, we'll get a new pathfinding challenge. So to do that, we want to have a randomized start. We're going to randomize start and end points. I'm going to say start, and it's going to be equal to, and these will be basically XY coordinates, or yeah, these will be coordinates on the grid. So we're going to say a rand range, and we're going to go from 0 to our grid size. And remember that rand range works the same way that range does, so it's going to go all the way up to our grid size, but it's not going to include the last number there. So it's going to go all the way up to 10, but not include 10. So our grid will be 10 by 10, but it'll start at 0. So we're going to say rand range, and we're going to do it again for the other coordinate. Okay. All right. And now, so that we're going to store that inside of a tuple. We're going to do the same thing for our goal here, where we want to go. Again, another tuple, and the first item in our tuple is going to be again rand range, where we want 0, grid size, and second item is going to be rand range 0, grid size. Okay, so we'll get two tuples with two random numbers between 0 and 9 for our coordinates on our grid. Okay, all right, now we need to make sure that our start and our goal isn't the same. If it is, we need to reset it. So here we're going to make sure start and goal are not the same. All right, because what will be the point there? So they'll be found very quickly. So while start is equal to goal, we're going to regenerate goal. So this might not run at all, but f when we generate this and we our start and we generate the goal, random things can happen and they could be exactly the same. If that's this case, we'll go into this while loop and it'll keep going until this is not true, when the start isn't the goal, and it'll keep generating new random goals. Okay? So next, what we want to do is set up our grid, okay? And we're going to actually create a function later on to do that. So right now, what we're just going to do is actually call the function that we're going to create later on. We're going to say set grid, and we're going to say start. We're going to send it's the start and the goal, and it'll set up our grid for our pathfinding algorithm. So it'll make the screen black. It'll basically just like cleaning off a chalkboard, so we can write new stuff on it. It'll draw the fresh grid, and it takes two arguments. Like I said, it takes our new start and our new end. Every time we press a button, we will get new start and new end, okay? And then it will also place the start and the end on our grid in red and blue, okay? Next, in our loop, we want to actually call our A-star algorithm. Okay, the algorithm will return came from, so we can actually use where it came from once it's finished running to trace its steps back to the start once it's reached the goal. Okay, we're going to call the algorithm. Again, this is something we're going to write later on. Make sure I put a note here, clear the screen, set the stage. Okay, now we're going to run a star algorithm and draw path. Okay, so first we're going to call the algorithm and have it save it turn into a variable. So we're going to say came from is going to be equal to a star search algorithm, and then we're going to give it a start argument and a goal argument. Okay, so when we create that function later on, those are the two parameters that we'll need. Then we're going to set current to goal, okay, so that we can backtrack from where the A-star algorithm found the goal, okay? So now we need to actually draw the path from the goal back to the start, and we're going to do that with a while loop here. So we're going to say while true, so this will loop forever until we break out of it. So we're going to say while true, and we're going to say pygame not draw, right? And then we're going to draw on the screen that we created earlier. We're going to draw blue, and then we're going to use the current, the first coordinate, times the cell size. For our rectangle coordinates, remember the way that rectangles are created, we need x1 and y1 and then x2, y2 positions. All right, so current 0 is going to be multiplied by the cell size. Make this a little bit smaller because it's going to go over a little bit. And then we need cell size. All right, we need to do pygame display update. So we'll actually update the screen and time delay, because this is going to run so fast that you won't be able to see it if we don't put a little bit of a delay here. Also, what we want to do, once we've drawn the square, we want to say update the current to came from current. This will make sense a little bit later on, but came from is actually a dictionary that's being sent back to us. So we're referencing the next thing in our dictionary so that we can go back to where it came from. So where the square or the cell that it came from, so we can trace our path back to the start. Okay, but we need a way to break out of this. So I'm going to say if current equals start, then we are going to actually do this all one more time so that we draw blue on our start. And then we are going to break out of this loop. Okay, now at the bottom of this while loop, after the for loop has run, we're going to do a pygame.display update to make sure everything updates properly. Okay, and then at the very end, like I said, we have our pygame.quit. All right, so now what we need to do is actually create our function. So we need to create our A-star search function, and we need to create our set grid function. So let's start with our set grid function. It's a little bit easier to understand. That's what we'll start with. We've done things like this in the past when we were doing other games. So we're going to create a function to clear screen and set up the grid. Okay, df for function defining our functions, set grid. It has two parameters, start and goal, and then we're going to screen fill with black, basically clear the screen, and we're actually going to create the grid here. So we're going to say for x in range 0 to window size, and again, we want the first item. We're going to say cell size. Okay, our step is going to be our cell size. Okay, and then we're going to say for y in range, we're going to say 0 to window size, the second thing in our tuple. In this case, it'll be exactly the same as our first thing because we have 500, 500, but you can change this to whatever you want to. This code will work properly because we're using the settings here that we set up here as opposed to hard coding it. So cell size will be our step because here as well. And then we're going to create a rectangle based on pygame.rect. We need an X and a Y for our rectangle, and then we need a cell size for the size of the rectangle. All right, so then we're going to say pygame dot draw to draw the rectangle. Right, screen right And then rect is what we're going to draw. We're going to draw it on the screen. The color is going to be white. The rect is what we're going to draw, this rect. And the border is just going to be 1. Okay. All right. So now that we have that, we also need to set our start and our goal, right? What was sent over. So we're going to visually represent the start and end points by coloring them. Red is going to be start, blue is going to be our end. So say draw start and end points here. And again, we're going to say pygame, draw, rect, then screen, red. Okay. And now we need a tuple here. And inside of our tuple, we're going to say start, get the first thing out of the start tuple, multiply it by the cell size, and then get the second thing out of the start tuple, and then start, then get the first thing out of the tuple, and multiply it by cell size, and then cell size. Okay, and so you don't have to type all of that all over again. We're going to basically do the same thing for our goal, but we're going to change this from red to blue, and we're going to change this from start to goal. So we're going to get the tuple that we sent over to this function for goal, get the second item and the first item. Okay, so cell size. All right, okay, so that clears our screen and it creates a grid. Now, what we need to do now is actually create our A* search. Okay, so we're going to do that here above the function we just now created. Okay, so this is our main workhorse. Of course, the A* algorithm, as we discussed is great because it's efficient. That means it finds the shortest path quickly without checking every single square on our grid. That's like finding the quickest way home without going down every single road. So think about how you could possibly use this in your real life. Maybe you're planning a community event and you need to figure out the quickest route to pick up all the supplies. You could use A* to do something like that. Okay, so when we create this function, we are going to have 3 data structures that are going to be our main ways of keeping track of everything inside of it. We're going to have a frontier list, which is basically just our to-do list. We have the squares that we want to check in our frontier. Then we have the came from dictionary, which is going to keep track of how we got to each square. And so we can find our way back when we return the came from to the main loop. And then we get the cost so far dictionary, which is like counting steps. It's keeping track of how long it took us to reach each square. And as a quick reminder of how the A* algorithm works, I'm going to play this quick video.
A* utilizes 3 main numbers to calculate the best path. The g-cost finds the travel distance from the node to the start node. The h-cost is the opposite, in that it represents the estimated travel cost from the node to the target node. The h-cost is optimistic in nature, so it will either be spot on or it will underestimate the cost. It will never give a cheaper than possible value. Take this grid for example. The h-cost of this node is 3 because it's 3 nodes from the target. But if we put an obstacle in the way, making 3 moves to the target impossible, the h-cost remains the same, as it was only an optimistic assignment. So to iterate, the actual steps required from any node will always be equal or more than the estimated h-cost. The f-cost is equal to the g-cost plus the h-cost. The lower the f-cost, the more attractive it is as a pathfinding option. The goal is to simply choose the lowest f-cost over and over until we reach the target node. Okay, let's look at a few examples of A* in action. Alright, so I'll begin by placing my target here and we'll begin pathfinding. So as you can see, all the nodes have a g-cost of 1 as we are just 1 node away from our start, but the h-costs vary depending on how far away they are from the target. So first we'll find our lowest f-cost, so this will be 4, and we'll choose this. So we will now move to this node and we will check our surrounding targets again, and we'll choose the lowest f-cost again. And as you can see, our g-cost is getting larger as we're moving away from our start position, but our h-cost is getting lower as we're getting closer to our target, and our f-cost will stay the same as we are just raising one number and lowering the other until we find our target.
Okay, so we are going to start with finding our function here. So A* search, remember we're going to send over the start tuple and the goal tuple when we call it. So those are the parameters. We called it from our game loop, or we called it inside of our game loop rather. So we're going to initialize our main data structures with starting points. Okay, first is going to be our frontier, as I mentioned, which is going to be all the nodes that we're looking at, and that's just going to be a list with tuples inside of it. So the first tuple is just going to be our starting point. We're going to have 0 for the priority, and then our start, okay, as the location node. Okay, all right. So this is actually the list that we're going to use the heap queue module to keep a priority queue. Okay, so that'll be our frontier. Then we're going to say came from, and this will be our dictionary, which is how we figure out where we came from. Okay, so start is going to be none. Okay, remember start is a tuple. So inside of this is when we randomly generated start inside of the game loop, it's randomly generated as a tuple with 2 numbers. So in memory, this will be the key. This is the first key value pair inside of our dictionary. It'll be a tuple, will be the key, and then the value is none, because this is where we start, so it doesn't come from anywhere. But as we add to this dictionary, we'll have key value pairs with the cell and then where it came from. So the next thing that's added to this list will be have start as its value, whatever cell it might be. So the cell would be over here, and then start would be where it came from, or whatever this tuple will be when we generate the numbers. Okay. Then we need to have our cost so far. So at the beginning, cost so far is nothing, right? So we're going to say cost so far, and this is going to be a dictionary as well. We will use start as the key, then start. So the cost so far is nothing. So again, the cost to reach each node, and then this is where each node was reached from, and this is the frontier, or the nodes to be checked, which we are saving a list, which is going to be converted into a heap. Okay. All right. So now we're going to do a while loop to basically search through the frontier. As long as there are places to visit or nodes in our to-do lists, we keep going. We're going to use a heap queue, heap pop, and it's going to be like asking what's the most important thing to do, because as I said, we're going to create a priority queue. It always gives us the square that's most promising to reach. And the reason it's going to do that is because that inside of this loop, we're going to calculate the cost as we saw in the video, and we're going to use that as the priority, the F cost specifically. All right, so we're going to say while frontier. So while this is true, while it has items inside of it, basically, we are going to remove the cell with the lowest F cost, or the priority, from the priority queue. All right, and to do that, we're going to say current cell that we're looking at, we're going to say heap queue dot heap pop, and we will say frontier as the item, and then what we want is the first thing from this popped off of this list. So we don't want what priority it is on the list, because remember, this is the entire item inside of the list. Each item inside of our list is a tuple. We don't want the priority in the list. What we want is the actual cell, which is right here. And for the first one, of course, is where we start. But as we go around this loop, it'll be whatever cell we're looking at. Okay. So we want the one. Okay. All right. So next we are going to basically color in the square that we're currently looking at as we're examining it. And also we're going to put a bit of a pause, like I said before, so that you can actually see it, because this would actually run so quickly that you wouldn't be able to see it. So I'm going to draw a rect and onto the screen, and we're going to make this green. So the current square that we're looking at has the lowest F cost. So it's the current, I'm going to say 1 times cell size, and then current 0. Remember, we got the current from our list, our priority queue. Okay, times cell size. So this is the one that we're examining right now, because it was the most attractive in our priority queue. When we're starting out, we're just starting out from the start. But as we're going through, you'll see that as this loop goes around, it's always going to be the thing that's the most promising based upon the score, or the cost that we put in. So we're going to do an update, and then we're going to see delay 100 again, so that it doesn't go too quickly. And we need to be able to break out of this. We're going to actually check to see if the current is equal to the goal. If this tuple is equal to whatever our goal is that we got sent over, then we can stop this loop. Okay, we can break out of it. All right, so next what we need to do is, based on the current cell that we're looking at, again, when we first start, it's just going to be the beginning cell. The current cell that we're going to look at, what we want to do is look left, up, and down. Okay, and we're going to use variables dy and dx, which you'll see more in calculus. D basically just means change, so the change in x and y. So we're going to create a for loop to do that. So we're going to say dx dy in, and then we're going to give it a list, and in that list is going to be a bunch of tuples basically. So we're going to say 1, 2, 3, 4 tuples, and we're going to say 1, 0, 2 to move, 0, 2. So we're going to say 1, 0 to move right, then negative 1, 0 to move left, and then 1 to move up, and then 0, negative 1 to move down. All right, basically, we're going to check all the cells around the cell that is our priority. Again, while we're first starting out, it's just going to be the first cell to see whether or not we want to move to it. So we're going to say next cell is equal to current cell 0, and then we're going to do change in dx, current 1, and then the dy, change in dy. Okay, so first we're going to look at right, left, up, down. Okay, when we go around this loop. So the first time next cell is going to be the cell to the right of the current, then it's going to be the left of the current, then up and down. So it's going to loop 4 times. All right, so we need to make sure that the cell that we're looking at isn't off of our grid. So we're going to create an if statement here. We're going to say f0 is less than or equal to next cell 0, and next cell 0 is less than our grid size, and 0 is less than or equal to next cell 1. You read this another way. You can say next cell 0 needs to be greater than or equal to 0 and less than the grid size. And next cell 1 needs to be greater than or equal to 0 and less than our grid size. Remember, these are tuples because these are coordinates in our grid, right? We just now created this tuple, the next cell tuple, from shifting when we go around the loop the first time, shifting to the right, okay? So if any of these are off of our grid, this if statement won't run, okay? So we're only going to do this if we're on the grid. So we need to calculate the new costs. Each time we move to a new square, it costs us 1 step, and we add this to our total step count, which is kept in our cost so far dictionary. We keep track of this cost to calculate the cheapest path. So we're going to say new cost equals cost so far, and then so far, and then we're going to use current as the key, and then we're going to say +1 to calculate the cost to current, or the new cost rather. And then we need another if statement here. We are going to ask 2 questions, basically. We're going to say, we're asking, first, have we ever been to the square before? The square meaning the next cell. And then second, we want to see whether or not this way that we've calculated is any faster than the old way. So we're going to say F's next cell, not in costs so far. So we haven't been there if we haven't been there before. So if the answer to either one of those things are yes, or new cost is less than cost so far for next cell, then we are going to we need to update the cost so far. So we need to say update the cost and add the square to the frontier for exploration later on. Okay, remember our frontier is our heap that we're keeping our priority cube. So we're going to say cost so far. We're going to use next cell as our key, and we need to save our new costs. Okay, now what we're going to do is calculate our priority for this cell specifically, next cell. And the way that we're going to do that is using our heuristic. And if you remember, we did this a little bit in our session. We discussed this a little bit in our session. The heuristic we're going to use
is the Manhattan distance. And our Manhattan distance is going to be our heuristic, or our best guess. Basically, you can think of this as like a GPS, so you're guessing the fastest route. And the reason it's called the Manhattan distance is because of the thought experiment that we have here. So think of yourself at First Street and First Avenue in Manhattan, in the city of New York. You want to get to 4th Street and 3rd Avenue. You can't go diagonally. So you'd walk up 4th Street first, that's 3 blocks, then over to 3rd Avenue, another 2 blocks. So you've walked a total of 3 + 2 = 5 blocks. And that's what this formula is doing. The absolute value of A0 minus B0, and again, A would be our starting point, B would be our ending point. And we say 0 because just like in our grid, or in our Manhattan example here, we have X and Y coordinates. So A0 minus B0, the absolute value is just a way of saying we're going to take any negative number and make it a positive. So -3 would be 3, -10 would be 10. So the absolute value of A0 minus B0 is our vertical distance from our start and our end. And the absolute value of A1 minus B1 is the horizontal distance. We add them together and we get our Manhattan distance. Here's a further explanation of this. So here's our grid. Think of this like a small piece of the city map. S represents our start point, E represents our end point. We're using X to represent the path. So we are on, say, 2nd Street and 2nd Avenue, and we want to go over to 5th Street and 4th Avenue. So we're going to go down 2 and over 3.
Actually define our heuristic, right? So outside of this, let's actually use it. First, we're going to say priority equals new cost plus our heuristic. We're going to send it over our goal as an argument in the next cell. I'm going to put it up here. So we're going to say define heuristic goal. Actually, we're going to say AB like we did in our example there. We're going to say A, B. Okay. All right. We're going to return, as I said, the absolute value of A0 minus B0 plus absolute value of A1 minus B1. Okay, so that's what our heuristic is going to do. It's going to return the Manhattan distance. All right, so now that we've defined that, we can go back down here and continue writing our A-star algorithm. So now that we have the priority, it's calculated using our heuristic. Remember, we have, and our priority can also be defined as our F cost, if you remember the video. So F cost, or priority, is equal to G cost plus H cost, right? Remember, go back to the video if you've forgotten. F cost is equal to the G cost, which is the new cost that we calculated up here, plus our H cost, or our heuristic cost. Right, so moving on. Now we need to add this next cell to our frontier with its priority, okay? So we're going to, here, now that we've calculated the priority, we're going to say heap queue. Up here we popped. Now we need to push onto the queue. Heap, push. And remember, frontier is the list we're going to push onto, and we're going to push on a tuple. And in that tuple, we need to send it the priority that we have just now set based on calculating the F costs. And then we need to give it the actual cell. So whatever priority this is, that's calculated, and then the cell that we're looking at. Okay. Now, what we need to do is update where we came from for this square in the came from dictionary. Okay. All right. So I'm going to say came from next cell equals current, right? So when we get into the loop itself, we pop off the current. That's what we're looking at, and then we're going left, right, up and down for each one of those cells. Left, right, up and down. The next, we're going to assign it to the variable next cell, where all of these cells that we're looking at came from the current cell, right? This cell came from the current cell. I hope that makes sense. All right. Finally, what we want to do is we want to color in the squares with yellow to show that this next cell is a candidate for the best path. Again, this is just to observe what's going on where we're running the code. We're going to say pygame draw.rect screen. We're going to color these yellow so you can see them as a potential candidate. And we're going to have a tuple here with 4 items. Make sure you have cell size, and then next cell 1 times cell size, and then next cell 0 times cell size. Okay. And just as before, we need to do a pygame display update, and then pygame time delay 100. All right. Now, after this for loop runs, what we want to do is reset the stage. So we're going to redraw. We're going to clear all these green, and the green current one that we're looking at, with the highest priority, and also the potentials that we colored yellow. So we're going to clear that. We're going to say here, we're going to reset the grid. We're going to set grid for next set of checks. So whatever the next priority is all the way up here at the top of the while loop, we want to reset the grid so that it gets highlighted with green, and we don't have the previous priority or the previous thing that we were checking highlighted in green. So we're going to set grid, we're going to run the set function that we created again, and we're going to give it the start and goal. Okay. All right. So now, once all of this is finished running and we actually have our F the current equals the goal, the final thing that we want to do is actually return the dictionary, the came from dictionary, because once the current reaches the goal, the came from dictionary will have a list of all the cells that lead back to the start. So I'm going to go back again. So make sure this is on the same line as the while loop. Okay. And we're going to say return. We're going to return the came from dictionary, which allows us to reconstruct path back to the start. Okay, so you're going to return came from. Okay, and assuming I don't have any typos, we can actually run this and see what we get. I do have a typo somewhere on line 71. Where's my typo? Pygame display update next cell, comma pygame display update. Where's my syntax here? Draw right screen yellow. I know where my syntax is. I'm missing parentheses here. Okay. And I'm probably missing one on 119 as well. Down here, 19. Yes, I'm missing a parentheses there. And then I'm missing one in 124 here as well. Okay. All right. So now we can actually look at our algorithm. And just as I said, if you press any key, it should start. Okay. We have a bit of an error here. Let's see. Tuple object not callable. This was on line 118. I think we have another typo. Okay. So did I not use current times 0, current 0 times cell size. So this is a tuple, but I'm getting the 1. So there seems to be an error here. Let's close this and stop the code and see what the issue is here. It was on 118. So it said something about a tuple. Let's see what that might be. This looks fine. Might be missing something obvious here. Getting and current. So the current should be a number, cell size. You know what it is? I'm missing a comma here. I'm also missing a comma here. So this is the surface we're going to draw on. This is the color. Then we have a tuple with what we're going to, for the coordinates for the squares. Okay. So let's run this one more time. All right. Press a key. There we go. Press a key again. We get a noob start and end, and it's searching and it finds it. Start and end. I'm searching. The green is the priority for checking. The yellows are the potentials that we could check. Okay. And it works. Searching. Green is always the priority that's coming off of our heap. Okay. And then when we get to our goal, we backtrace. All right. So I'm going to stop this and show you, as I said before, that you can increase this because everything is based on these constants. increase this to, say, 20, the code should work just the same, just with a 20 by 20 grid instead of a 10 by 10 grid. Okay, all right, so now, okay, and again, remember the green is the priority, and the yellows are the potentials, the next cells, if you remember from the code. The green is the current, and then we're searching left, up, and down, and recalculating the scores based on the distance, the heuristic that we use to calculate the F cost. Okay, and that's basically it. You can play around with this, and of course, as I said, for your homework is to add obstacles to your grid here.